Alright, now we're going to discuss carbonyl compounds. As the name states, we're going to talk about carbons containing this functional group right here, C double bond O, and that is the carbonyl functional group. Although some people would prefer to call it as a keto group, people would then mistake that probably for the group only seen in ketones, but it's not the case. But in any way, we will see that here we have a partially positive carbon and a partially negative oxygen. Here we have two types of carbonyl compounds, and the only point of difference is this part here. Here we have R and H. Here we have two different R groups, or they can be the same, but the point is they're both R groups. Now, here we see that the functional group is simply the carbonyl group, or if they say this is a keto group, this is because this general pattern is what we see for ketones. But this is different. It has the carbonyl group, yes, but then again, there is a functional group in the likeness of this C double bond O, then single bond H, which actually acts as a standalone functional group. And this is actually called the formyl group. If it's condensed, it will be something like CHO. Now, this is the functional group for the other class of carbonyl compounds known as aldehydes. So, they have a similar carbonyl group, yes, but first things first, let's talk about what makes them different. Well, in aldehydes, noticingly, there's another H here. I'll try to find a certain paper in order to explain something. Here, I found it. We said that if we have an aldehyde, it can be further oxidized to another compound by virtue of sacrificing the H in order to be oxidized further. And from an aldehyde, actually, if we oxidize it further, it will become a carboxylic acid. Ketones, on the other hand, do not have that capability. Alright? When you try to oxidize a ketone, nothing will happen, because when you have a ketone, you don't have any more hydrogens to sacrifice for oxidation. So here, if you turn this H into an OH, what do you get? COOH. So this means that the difference is that ketones are not oxidizable. Aldehydes are oxidizable. And what are they oxidized to again? They are oxidized to COOH, carboxylic acids. And this is the property which ketones do not possess. Now, let's go to the similarity. They have this C double bond O, right? Let's say we have an attacking group. By the way, since this is partially positive, we assume that the attacking group would be either neutral or partially negative or negative, and that is a nucleophile. Yes, so we have a nucleophile attacking. Now, we know that the end product of this is something like carbon having a bond with a nucleophile. Now, in the case of this double bond, we should be able to recall that one of these bonds is sigma, one of this is pi. We cannot depict that just in this, double bond. They both look the same, but we should assume that as long as there is a double bond, one of them is pi, and we know that the pi bond is a weaker bond. Now, if we have a bond with a nucleophile, if we have the carbonyl carbon bonding with a nucleophile, this bond is sigma. And if we compare this sigma bond to the nucleophile and this pi bond to the oxygen, this nucleophile is stronger. So what happens? Actually, since we know that carbon here, let's have a ketone here. The carbon here cannot give away both of this. Okay? So what happens? The carbon will now resort to breaking this pi bond in order to give way to the nucleophile, which is trying to connect with the alpha, or that is trying to connect with the carbonyl carbon. So meaning that there is this pi bond that's being broken, and at the end this will become obliterated or something, eliminated that is, in order to come up with a final product of this. And in order to fill up this oxygen, let's add an H. This is the final product. So you see, we sacrificed the pi bond in order to form another bond. So we say, let's try to say this is A, this is B. We added B to A, yes, and we came up with a combination of the two. So what scheme is this? Is this addition, elimination, substitution? And it's obvious, this is addition. So let me make it clear that the reaction mechanism common for aldehydes and ketones is nucleophilic addition. As usual, I'm going to encircle it in a very slow manner, in order for you to recognize that this is indeed the mechanism for aldehydes and ketones. Now, let's go to specific nucleophilic addition reactions, and I'm going to, perhaps I'll just use ketones to make things uniform. I have 3 general types of reaction. No, I'll make it 4. Okay, there are actually 4. So let's start out with the first type. And the nucleophile in this case is simply water. And I'll draw it in its full glory. Alright, water. So again, as I said, one of the pi bonds will be sacrificed. Alright. Water will form a bond. The part here of the oxygen that will, the part here of water that will bond is one of the lone pairs. One of the lone pair will become untouched, and both hydrogens will become untouched as well. Here, oxygen will have 3 bonds, and you know that oxygen can only accommodate 2. This becomes positive, this oxygen becomes negative. In order to compensate for this difference in charges, oxygen can be like, hey, hydrogen, I'm kicking you out, and you could just go to the oxygen here who wants an electron, who wants a proton. Okay, so hydrogen will be like, okay, I'll go here. So hydrogen becomes removed from this area, and so as a result, what would be the product? R. So let's just copy this. O, OH, OH. So this is the original water molecule, HO. Now it's become like this, and this is, if you recall, this is a 1,1 diol. Okay, or actually in this case this is not 1,1, but the case is the OHs are in the same carbon. You could also call this a CHEM diol, but in this case we could call it a hydrate, since this is the product when you hydrated an alkane, or an aldehyde or a ketone. Now what if we, let's put a division here. What if we instead use an alcohol, ROH? Same thing, we'll draw this, one of the bonds will break, then the lone pair of the oxygen will react, and then since there are 3 bonds, oxygen will kick out the hydrogen will go up, and then the product will be something like this. Let's draw it. R, then O, then ORH. So the difference between the hydrate and this one is, here we have 2 H's, here we have 1 OH and 1 OR. Since we have a combination of this, we could say that this is a hemi something, and actually the name of this one is a hemiketal. This is a hemiketal because we started out with a ketone, but if we started out with an aldehyde, we will call this a hemi-acetal. Hemi, why? Because it's partial. There's something that you could do more to this after, and that is, you could actually make this OH also like this one, which is an OR. So let's try to do that. Let's use another color. This is the second mole of the alcohol. What would happen? R prime, OR, then what happens? OH will be removed. OH, is like here, and there's an impending ROH that's going to attack. Okay, so originally the bond is OH, but then again this one is attacking, and carbon cannot anymore accommodate both because it will then have 5 bonds. So between OR and OH is more is a better leaving group because OR is stable. The R stabilizes the oxygen here, and oxygen will be like, it's okay for me to stay with carbon, but OH here will be like, hey, I can just leave if you want. So oxygen here leaves. Okay, so what would happen? The oxygen here will be having a covalent bond, but then again we have 3 bonds again. In order to resolve that, oxygen will also kick H. So as a result, we have this and this. If we combine this H and then the OH from the original hemiketal, we will now form water as a byproduct. But the point is, you released something. Okay, there is a kind of elimination. So this time, it's not anymore simply nucleophilic addition. Since you have a byproduct that is water that you removed from the original hemiketal, the reaction mechanism is now this nucleophilic addition followed by elimination. And this time, since the product, let's draw the full product here clearly. This is from the second mole. This is from the first mole of the alcohol. We have 2 ORs here. This is now what we say, not anymore hemi, not more partial. It's a complete ketal. Or if the reagent was an aldehyde, an acetal. Now, let's go to the third type of, or for the third nucleophile. And that's actually an amine, or just to make it simple, ammonia. Same thing will happen. The pi bond will break in H3. Since nitrogen can accommodate only 3 bonds, one of the hydrogens will be removed. They will go up, and here you would expect, like in the previous, in the hydrate formation or the acetal formation, you would produce something like, just this. This is, well, if you say you want to name this is an amine, this is an alcohol, you could try to call this an amino alcohol. But the thing is, this does not exist because an amino alcohol is very unstable. It will not last long. So in short, this will, no more ink. Let's just use this one. This will not last. So what happens? Carbon here will have to choose between oxygen and nitrogen, which to form a bond with, and one will have to go. And between the two, carbon would be like, hey, oxygen, madamot yan, oxygen would take away my electron, so I'll just bond with nitrogen. So what happens? Oxygen leaves, and oxygen is like, okay, fine, if you don't want to bond with me, I'll just take away your electrons, and oxygen will be negative, and then carbon will be positive, and then nitrogen here has a lone pair. So what happens? We have a negative charge here, we'll have a positive charge here. I think you know what's going to happen. In order to cancel the imbalance in charges, the double bond will form. Okay, that's not yet the final. Remember, nitrogen here will then have 4 bonds, 1, 2, then 2 hydrogens. So it will take away 1 hydrogen. So 1 hydrogen will go away. OH here and H here will combine to form H2O also as a byproduct. And since again we have a byproduct in this reaction, we have eliminated water, the reaction mechanism again is ANE. And this particular product wherein we have a double bond to a nitrogen, it's not anymore an amine. Okay, we call this amine with a double bond something else. We call this an imine. So basically, imine is an amine having a double bond. here, since we started with a ketone, we can call this a ketimine. But if we started with an aldehyde, we call it an aldimine, just like, you know, the way we named acetals or ketals. Finally, the last electrophilic addition reaction we could use for aldehydes and ketones is the Grignard reaction using a Grignard reagent. Basically, the Grignard reagent looks something like this. R MgX. As compared to carbon and a halogen, X here is a halogen. As compared to any of the two, magnesium is less electronegative. What does that give us? Very partially positive charge here. Partial negative. You will see here the carbon is partially negative. And so what happens? So now we will have, let's try to have an RMgX here. It will become our nucleophile. Then let's bring back our carbonyl compounds. This time I want to start off with the simplest carbonyl compound possible. This is methanol, or its trivial name is formaldehyde. What happens? We follow the same mechanism. A pi bond will be broken, then the R will bond MgX. Then this MgX will be removed by virtue of adding water. So then what will happen is that you will have a product that looks something like this. HCHO. Then let's just add H to make this oxygen happy. Then R. What is this? ROH. This is an alcohol, right? This is an alcohol, but this is not just an alcohol. This is the alpha carbon, right? Then this is bonded to one R group. So how do we call this if it's bonded to one R group? If you say primary, yes, this is correct. This is a primary alcohol from methanol. Now, let's try to make one of these H's an R group, and this would now become an aldehyde other than methanol, or other than formaldehyde. Let's use the same Grignard reagent. So basically what happens, we remove one pi bond, we make it H, then the R from this will bond. Now we have the alpha carbon containing two R's as its substituents. We now form a secondary alcohol. Simple. And now let's turn this H into another R to form a ketone. Then let's use the same Grignard reagent, R MgX. And as a result, I think you know what's going to happen. OH R. So this is the alpha carbon. It's bonded to 1, 2, 3 substituents that are carbons also. We produce a tertiary alcohol. So again, to repeat, if we start out with methanol, we produce a primary alcohol after Grignard reaction. From aldehyde, we produce a secondary alcohol, and from ketone, we produce a tertiary alcohol. And that's the last general reaction for nucleophilic addition. And by the way, since we used water to remove MgX, we eliminated this one. So again, the mechanism of action is not just nucleophilic addition. There is a removal of something. It's also ANE. And so that's it.